Hey everyone! A while ago, I made a video talking about which Ice Age animals would be the easiest to bring back. So, I thought I'd do a follow-up with an Ice Age Resurrection tier list. The easiest to bring back will be the S tier, while the hardest will be the F tier. Where a given species falls on the list will depend on two main factors. One is how well preserved the best remains we have from them are, i.e. how good the DNA we have from them is, and the other is how closely related the closest living relative of the species in question is to them. The benefits of having a closely related living relative are twofold. One is that it gives you a good reference genome to align the DNA fragments from the extinct species, and second, it could act as a surrogate mother for a clone. We'll start with the iconic woolly mammoth, which I'll put in A tier. We found many mammoth remains frozen in permafrost, so we've got a lot of good DNA from them. But on top of that, we found a mammoth in Siberia with a bit of skin tissue which was freeze-dried. This preserved its genetic architecture, which could itself possibly be used as a reference genome. The closest living relative of the woolly mammoth is the Asian elephant, and they seem to have split from each other 6.7 million years ago. Asian and the more distantly related African elephants have been known to give birth to hybrids, or a hybrid, an individual known as Madi who was born in 1978. However, he died shortly after birth, and this is likely the result of complications you get when you cross such distantly related species. Such complications could have come about from two factors. One is that the homologous chromosomes that they get from each parent don't properly complement each other due to differences in their genetic architecture, i.e., where the various genes are positioned on the chromosomes. The other problem is molecular incompatibility between the embryo and surrogate mother. The placenta, which facilitates the transfer of nutrients between the mother and fetus, is made of both the fetus and mother cells. The two varieties of cells have to be able to communicate properly, and if they can't because of differences between the signaling molecules each employ, it will result in complications, which can ultimately lead to a miscarriage. The first issue isn't a problem with a cloned animal, but the second is even worse with it. Madi was born prematurely, implying pregnancy complications associated with the molecular compatibility were a factor in his death. This means that if we made a mammoth embryo and implanted it into an Asian elephant surrogate mother, there will probably be complications associated with the pregnancy. Now, it is true that mammoths were more closely related to the Asian elephant than the African elephants are, but African and Asian elephants split from each other at most 9 million years ago, only 33% older than the mammoth Asian elephant divergence date. Also, the fetal cells of Madi's placenta were genetically half Asian elephant, while a mammoth clone would be pure mammoth. So, I'd say a mammoth cloned in an Asian elephant surrogate mother would be even more likely to run into pregnancy-associated complications than an African-Asian elephant hybrid. This means that if we are to successfully clone a woolly mammoth, we'd have to start with an Asian elephant woolly mammoth hybrid, which would be carried by an Asian elephant mother, which could then act as a surrogate mother for a pure woolly mammoth clone. Although, since Asian elephants are only slightly more closely related to woolly mammoths than they are to African elephants, an Asian woolly hybrid would likely run into the same problems that Madi did, so we'd probably have to start with an individual that's 1/3 woolly mammoth and 2/3 Asian elephant. This animal would then give birth to an individual who is again genetically engineered to be 2/3 woolly mammoth that would finally give birth to a pure mammoth clone. While we have exceptionally well-preserved remains from the woolly mammoth, problems associated with an Asian elephant carrying a clone made me put it in the A-tier section. The next animal, however, is a solid S-tier, and that is the cave lion. We've recently found mummified cubs which were frozen in Siberian permafrost, including a 28,000-year-old individual which has been described as the best preserved Ice Age animal yet discovered. From these, we can get high-quality DNA. Although these Ice Age mummies weren't freeze-dried, which would have preserved their genetic architecture, their similarities with the living lion would offset this. There are a variety of estimates as to when cave lions and African lions diverged from each other, but it was certainly in the last million years. This means the genome of a modern lion could be used as a reference to assemble the genome of a cave lion with DNA extracted from the frozen cubs. Meanwhile, it remains to be seen if the frozen mammoth chromosomes, or the genome of a living Asian elephant, would act as a better reference genome to reconstruct the woolly mammoth's genome. Also, while only one Asian African elephant hybrid was ever documented, and it died shortly after birth, modern lions and the more distantly related tigers hybridize regularly in captivity, producing ligers and tigons, meaning the risk of complications associated with having an African lion act as a surrogate mother for a cave lion cub is pretty low. It is true that the fetal cells of a tigon's placenta will be genetically half modern lion, while those of a cloned cave lion fetus will be pure cave lion. But the tiger-lion divergence is estimated to have occurred 3.7 million years ago. This puts the cave lion-modern lion split closer to the present day than it is to the lion-tiger split, suggesting that a cloned cave lion fetus would be less likely to suffer from neonatal complications than a lion-tiger hybrid. This is in contrast to the Asian elephant-mammoth divergence, which was closer in time to the African-Asian elephant split than it is to the present day. So, we could get a pure cave lion in a single generation, thus it's an S tier. Next up, we have the American lion. Like the cave lion, it's a close relative of the modern lion, but no soft tissue remains have yet been found. However, advances in the field of genetics have allowed us to extract DNA from ancient bones and teeth, although the bits of DNA we get from them are usually more fragmented than we get from soft tissue. This tempts me to put in the B tier section, but we do have an intermediate. While already being a close relative of the living lion, the American lion was even more closely related to the aforementioned cave lion. As discussed before, it would be one of the easiest Ice Age animals to resurrect, so once we do that, we could use its genome as a reference. So, although assembling the more fragmentary DNA from the American lion, while using the modern lion as a reference genome would be more difficult than assembling a cave lion genome with the larger DNA fragments we can get from the mummified cubs, this problem could be attenuated by using the even more closely related cave lion genome as a reference once it's brought back. This is the whole stacking resurrections approach I mentioned in my earlier video. Because we can use the cave lion as an intermediate, the American lion gets bumped up to A tier. Now, on to another icon of the Ice Age, the woolly rhino. This species inhabited much of northern Eurasia during the Pleistocene, and like the mammoths, we found mummified remains in Siberian permafrost. But we haven't yet found any remains which preserved its genetic architecture. Furthermore, its closest living relative is the Sumatran rhinoceros, and while mammoths and Asian elephants split from each other 6.7 million years ago, woolly and Sumatran rhinos last shared a common ancestor 9.6 million years ago. This means you'd likely run into even more complications if you had a Sumatran rhino act as a surrogate for a woolly rhino clone. So, I'll put it in B tier. Now, back to mammoths. The paleontology enthusiasts out there probably know that woolly mammoths weren't the only species roaming around in the late Pleistocene. In North America, there was the larger Colombian mammoth. We have not found any mummified remains of the Colombian mammoth, meaning any DNA would have to be taken from bones. This would nominally put it in D or E tier. However, it's closely related to the much easier to resurrect woolly mammoth. So, as is the case with the cave lion and American lion, once we have a woolly mammoth, it could act as a reference genome and surrogate mother. We found specimens who appear to have been woolly Colombian hybrids, implying the two species had a very similar genetic architecture, and there would be a low risk of complications in pregnancy. So, the Colombian mammoth will go into the B-tier category. Next, we'll look at the animal that started this whole discussion, the direwolf. No mummified remains have yet been found, and there's no reason to suspect we'd find them. So, any DNA that we get would have to come from bones, i.e. be highly fragmented. It had long been thought that having the gray wolf as a similar reference genome would offset these problems. Many phylogenies based on morphology indicated that the gray wolf was even more closely related to the dire wolf than it is to the coyote. However, once we got DNA from direwolf remains, we learned that instead of being a close relative of the gray wolf, the direwolf last shared a common ancestor with it 5.7 million years ago, with the gray wolf being more closely related to the painted dogs, dholes, and jackals than it is to the direwolf. So, what is the closest relative of the direwolf? Well, there isn't a single species, as the direwolf was the last of a canid lineage which inhabited the Americas. Instead, it was collectively the clade, which includes the gray wolf, the painted dog, dhole, and the jackals. Because they split off so long ago, it will be difficult to align the genome of a direwolf using any of their genomes as a reference, and even if you could make a zygote clone of a direwolf, if you used a gray wolf or any of its close relatives as a surrogate, you'd probably run into complications during pregnancy. So, I'll put the direwolf in D tier. Apart from the cave lions, we've recently found the cub of another felid in permafrost. I'm of course referring to the Scimitar Tooth Cat Homotherium. We can of course get high quality DNA from this specimen, but unlike the aforementioned cave lion, Homotherium split off from all living felids some 28 million years ago. This means you'd run into even more difficulties aligning the DNA than you would with a mammoth and an elephant, and you'd have far more problems using a living cat species as a surrogate. Because of this, the Scimitar Tooth Cat gets bumped down to C tier. But what about the more famous saber-toothed cat Smileodon? We haven't found any mummified remains from it, so we'd have to use the highly fragmented DNA from bones. But, since we have soft tissue from another Macariodont, the Scimitar Tooth Cat, couldn't we use the stacking resurrection approach with Smileodon? Well, the problem with this is that while Homotherium was more closely related to Smileodon than any modern felid, the two diverged from each other 20 million years ago, so they aren't that much closer. This means that a resurrected Homotherium wouldn't be that much better as a reference genome or a surrogate mother than any modern large felid. On top of that, we know much more about how living felids go through pregnancy, and thus what kind of complications we'd run into if they were carrying the fetus of a distantly related species. This wouldn't be the case for the Scimitar Tooth Cat, so no, the stacking resurrections approach wouldn't be viable with Smileodon and Homotherium, putting it in E tier. What about the last Ice Age icon, the ground sloths? Well, there's quite a lot to unpack for these strange creatures, most of which bodes ill for the possibility of bringing them back. For one, ground sloths are not a single monophyletic grouping. Instead, some are more closely related to the modern two-toed tree sloths, while others are closer to the three-toed tree sloths. Although one lineage, known as the megalocnids, split off from all other sloths, ground, and tree first. These were smaller than most other ground sloths, growing up to the size of American black bears, and they inhabited the Caribbean islands. Having diverged from all living sloths over 40 million years ago, the modern sloths would be a poor reference genome and surrogate parent for any cloned megalochnid. They also lived in a hot humid environment, which is not exactly conducive to the preservation of DNA. However, while most ground sloths had gone extinct around the end of the Pleistocene, the megalochnid survived into the mid-Holocene, finally dying out 5,000 years ago. Because of this, we've been able to get DNA from the megalochnid remains, so they're spared from going into the lowest tier, and instead go into E tier. While most late Pleistocene ground sloths lived in tropical and subtropical regions, some did reach into more polar latitudes. One of these was Milodon, which lived in Patagonia. Here, the cold, dry climate preserved bits of skin in caves. So, we have a source of good DNA, and it's estimated that Milodon and the two-toed sloth split from each other roughly 30 million years ago. This is comparable to the scimitar tooth modern phelodivergent state, and, given that we've also found mummified remains of the scimitar tooth cat, Milodon goes into the same C tier. There were also some other species of ground sloths who were closely related to Milodon that lived up to the late Pleistocene. One of these was Paramodon, or the Harlins ground sloth, which inhabited most of the continental U.S. I looked through the literature and have not been able to find any attempts to extract Paramodon's DNA from its bones, but it lived in fairly cool climates, which would have facilitated the preservation of DNA, which could be used to clone it. It's estimated to have shared a common ancestor with Milodon some 8 to 9 million years ago, making the stacking resurrections approach viable should we bring Milodon back. So, I'll put it one level below Milodon in D tier. Although, I should note that because Paramodon split off from Milodon earlier than most other animals we're using the stacking resurrections approach for, it gets into D tier by only the slimmest margin. Another species which is closely related to Milodon was Glossythetherum. This species also lived in South America, mostly living in the Pampas region, but with some populations inhabiting the more northerly coastal regions of South America. So, it basically lived in warm and humid to intermediate environments, i.e., not the best for the preservation of DNA. While not as bad as the Caribbean, the youngest Glossythetherum remains are twice as old as those of the youngest Caribbean ground sloth remains. As far as I can tell, no one has yet got DNA from Glossythetherum remains, but then again, a possibility is that no one has yet tried. However, I looked through the literature to see if anyone has gotten DNA from Pleistocene-aged bones from other creatures in the areas Glossythetherum lived in. They have gotten mitochondrial DNA, but they couldn't get any nuclear DNA. Mitochondrial DNA is stored in organelles in the cells known as mitochondria. DNA in the nucleus is arranged in a series of linear strands, i.e. chromosomes, while mitochondrial DNA is comprised of a single circular strand. This makes it more resilient to degradation than nuclear DNA. While mitochondrial DNA can be used to infer an animal's evolutionary history, it is nowhere near enough to clone it. However, remains from Glossythetherum have been identified from the coastal arid regions of Peru. Recent discoveries have shown that even in warm climates, arid conditions can preserve Pleistocene-aged nuclear DNA, so there is a possibility that we could get nuclear DNA from some of the Glossytherum remains dug up in western Peru. This, along with the fact that the stacking resurrections approach could be utilized with it in Milodon, puts Glossythetherum in E tier. Interestingly, the revelation that DNA could be fairly well preserved in warm, arid climates was made when studying the remains of another ground sloth known as Nothrotheriops, or the Shasta ground sloth. This species inhabited the southwestern U.S. and northern Mexico, and it seems to have frequently used caves for shelter. Many of these caves were in bedrock composed of sandstone and limestone, which desiccated large quantities of ground sloth dung, which has given us a unique insight into their diet. It's from this dung that we've been able to extract nuclear DNA. We've also found bits of preserved soft tissue from the Shasta ground sloth in these caves. But while we have found large patches of Milodon skin in Patagonian caves, what we found from the Shasta ground sloth are some tendons and small bits of skin, which are mostly fur. So, the DNA we can get from these soft tissue remains probably won't be much better than what we got from the desiccated dung. While Milodon was more closely related to the modern two-toed sloth, the Shasta ground sloth's closest living relative is the three-toed tree sloth. It also split from it roughly 30 million years ago, and, since any DNA we can find from it will be in poorer condition than that of Milodon, the Shasta ground sloth goes into D tier. Arguably the most famous species of ground sloth is Megatherium, or the giant ground sloth, although the largest species was the slightly larger and closely related Arematherium. Megatherium lived in the central part of South America, while Arematherium had a much more tropical distribution, inhabiting northern South America, Central America, Mexico, and Florida. Like the Shasta ground sloth, Megatherium and Arematherium were on the three-toed branch of the sloth family tree, and were more closely related to the Shasta ground sloth. So, is there a possibility of utilizing the stacking resurrections approach with them? Well, the split between the Shasta and giant ground sloths is estimated to have occurred more than 20 million years ago, putting it closer to both of their split from the three-toed tree sloth than the present day, hence I wouldn't bank on it. And, even if they shared a common ancestor to the Shasta ground sloth closer to the present day, in order for the stacking resurrections approach to be viable, you need DNA to work with in the first place. Given that Arematherium lived in warm, humid climates, I doubt we could get nuclear DNA from it, so it goes into the F tier. Megatherium remains have been found in drier climates, but since the stacking resurrections approach wouldn't be viable with it, this possibility isn't enough to bump it up a level. As such, both species of giant ground sloths go into F tier. The last species of ground sloth we'll talk about is the Jeffersons ground sloth, or Megalonyx jeffersoni. Like the Shasta and giant ground sloths, they are on the three-toed branch of the sloth family tree. It was actually more closely related to the living three-toed tree sloth than it was to the previously discussed species, but again, not by much, because the Jeffersons ground sloth split off from it shortly after they shared a common ancestor with the giant ground sloth and the Shasta ground sloth. So, the modern sloth's genome wouldn't have been that much better a reference to reconstruct the Jeffersons ground sloth genome than it would the Shasta ground sloths. But what about the quality of DNA we have to work with? Like the Harlins ground sloth, the Jeffersons ground sloth lived over the continental U.S. during the last ice age, which includes both cold and arid climates, which would have preserved some of its DNA. But it doesn't appear to have utilized caves like the Shasta ground sloth, so any nuclear DNA we get will probably be more fragmented, so I'll put it in E tier. Going back to the predators which terrorized the Ice Age world, we'll next look at Arctodicimus, or the giant short-faced bear. This species lived in northern Mexico, the continental U.S., Alaska, and the Canadian Yukon. Its closest living relative is the spectacled bear of South America, having shared a common ancestor some 4.8 million years ago. This is comparable to the 5.7 million year old gray direwolf divergent state, which, on its own, should put the short-faced bear in the same D tier. However, While we've only found teeth and bones from the short-faced bear so far, it lived in Alaska and the Yukon during the last glacial period, where we found many similarly aged mummified remains in the permafrost. So, it's a very real possibility that we could find frozen soft tissue from the short-faced bear, which we could extract high-quality DNA from. This possibility bumps it up to C tier. Now, it is true that the Jeffersons ground sloth's range extended into Alaska, but it only did so during the interglacial periods, and ice mummies from that age are very rare. Although, I feel there's another factor I should mention which pertains to the short-faced bear. This is whether or not we actually want it back. According to some Native American folklore, attacks by bear-like monsters blocked their passage into the Americas through the inland corridor. Hence, they took the nearshore route along the Alaskan Panhandle British Columbian coast. And this does explain a disparity in the archaeological record, where the oldest human remains in the continental U.S. predate the oldest found in Alaska. While there would have been short-faced bears in what is now the continental United States, these were not as carnivorous as those in Alaska. Also, further south, there would have been forests to take cover in. During the last glacial maximum, Alaska was covered in the wide-open mammoth steppe, where there was nowhere to hide. So, maybe I should have included the "do we really want to bring back such a fearsome creature" criteria in this tier list. In South America, there was another genera of large bears known as Arctotherium, who were also related to the spectacled bear. Earlier in the mid-Pleistocene, one species, Arctotherium augustidens, surpassed the short-faced bear in size. However, its descendants who survived at the Pleistocene-Holocene boundary were closer in size to modern brown bears. But how easy would they be to bring back? They were more closely related to the spectacled bear than Arctodus was, but only slightly, having shared a common ancestor with it 800,000 years after both of them shared a common ancestor with Arctodus. This puts it in the D tier with the direwolf. It is true that some species of Arctotherium lived in Patagonia, where we found mummified remains from Ice Age animals. However, these are nowhere near as common as the permafrost mummies are in the Arctic region. So, the odds of finding preserved soft tissue from Arctotherium aren't good, and not enough to bump it up to C tier. While the short-faced bear stalked the land in the Americas, in Eurasia, the most iconic Ice Age bear was the cave bear. Unlike most other Ice Age megafauna, the cave bear seems to have gone extinct around the time of the last glacial maximum 25,000 years ago. Also, its remains are rare in areas with permafrost present. On the surface, this would seemingly make it harder to resurrect than the short-faced bears. However, it frequently hibernated in caves where its remains have been found, hence the name cave bear, and many of these were in cool alpine environments, ideal for the preservation of DNA in teeth and bones, and from these we have actually gotten high-quality DNA. Furthermore, it was much more closely related to the modern brown bear than either of the short-faced bears were to the spectacled bear, having shared a common ancestor with it roughly 1.3 million years ago. Brown bears can hybridize with the more distantly related American black bear with minimal risk of prenatal complications or birth defects, meaning a brown bear would be a suitable surrogate for a cloned cave bear, hence it goes into B tier. Let's now look at an animal that would probably be pretty easy to bring back, the steppe bison. This species inhabited much of the mammoth steppe, i.e. Europe, Siberia, and Thuringia during the last ice age, and we've been able to find mummified remains of them frozen in the permafrost, including the famous blue babe specimen. It was even more closely related to the modern bison, both European and American, than the cave lion is to the modern lions, having split off between 200 and 100,000 years ago. So, it would be very easy to reconstruct its genome using the living bison species as reference, and they could easily act as a surrogate, so the steppe bison goes into S tier. Another extinct bison species was the Longhorn Bison, or Bison latifrons. It lived in the continental U.S., so we're unlikely to find mummified remains, but it was even more closely related to the American bison than it was to the steppe bison. This is enough to put it in A tier. The third species of bison is Bison Antiquas, which also lived in the continental United States during the last ice age. Instead of merely being a close relative of the modern American bison, it's believed to have been ancestral to it. This will make it easy to reconstruct its genome, even from highly fragmentary DNA, when using the genome of an American bison as a reference. So it goes into S tier, and is the only Ice Age animal we don't have mummified remains from to go into this category. Now, let's take a look at the other Pleistocene elephant species that roam the Earth, starting with the American Mastadon. It lived throughout the continental U.S. during the Pleistocene-Holocene boundary, including fairly cool places near the Canadian border, which could have preserved DNA that could potentially be used to clone it. However, while the more famous mammoths were a descendant of the common ancestor of all living elephants, the Mastadon split off from them some 20 million years ago. This would make any living elephant a poor surrogate for a cloned individual and reference genome to reconstruct the Mastodon's genome. Because of this, I'll put the American Mastodon in E tier. Another prehistoric group of elephants were the enormous straight-tusked elephants of Eurasia. Most of the species died out before the mammoths and mastodons did, with the mainland species going extinct just before the last glacial maximum, roughly 25,000 years ago. However, a dwarf species survived on Cyprus until about 11,000 years ago. We've got some nuclear DNA from both the mainland and insular species. Which source would be of better quality? It's hard to say because while those from the European mainland will be older, they're also in a cooler environment, which would be better at preserving DNA. Either way, we'd probably get more fragmented DNA than we could get from the American Mastodon. You might think this disadvantage could be offset by Paleoloxodon being, like the mammoths, a descendant of the common ancestor of all living elephants, but there's a problem. Over the last century, paleontologists debated whether Paleoloxodon was on the Asian or African branch of the elephant family tree, because they had morphological features characteristic of both. Analysis of their DNA revealed that the straight-tusked elephants had a very complicated evolutionary history. They initially split off from the base of the African branch before interbreeding with the progenitors of mammoths before finally interbreeding with the ancestors of the African forest elephant after it split off from the bush elephant. This admixture will certainly make reconstructing the genome of Paleoloxodon difficult because you wouldn't know where to use African or Asian elephants as a reference. This complication bumps it back into E tier. The other two groups of late Pleistocene elephants were the Gomphotheres and Stegodons. Like the Mastodon, they were not a descendant of the common ancestor of all living elephants, but they were more closely related to them than the Mastodon was, with Stegodon being more closely related to modern elephants than the Gomphotheres. However, they both inhabited warm and humid climates, with Gomphotheres living in northern South and Central America, and Stegodons living in Southeast Asia in the late Pleistocene. So far, we've been unable to extract nuclear DNA from either of their remains. This leaves us with nothing to work with, putting both Stegodon and the Gomphotheres in F tier. So far, we've mostly discussed extinct mammals, but what about birds? Perhaps the most famous Ice Age bird was the teratorns. Teratorns lived over much of the continental U.S., including cool and arid regions up to the Pleistocene-Holocene boundary. While such climates are conducive to the preservation of DNA, flight-capable birds have hollow bones. This poses two problems for the preservation of DNA. First, it means there is less bone marrow, i.e., soft tissue, and thus less genetic material in the bones in the first place. Second, it means the bones break apart faster, more rapidly exposing what DNA is present to the elements. As such, it's doubtful we get any nuclear DNA to work with for cloning the teratorns, so I'll put them in F tier. Going back up to the Arctic, we find the muskox. During the Pleistocene, a larger species known as the Harlins Muskox, or Butherium, lived further south, inhabiting pretty much all of the mainland U.S., including Alaska. It appears to have preferred woodland habitat, but its remains have been found in Alaska dating to the last glacial period when it was covered by mammoth steppe, indicating the Harlins Muskox could have also lived in grassland. Among their remains found far north was a mummified specimen in permafrost. This can give us high-quality DNA. Furthermore, molecular clock estimates have put the modern Harlins Muskox divergence date at around 250,000 years ago. This will make the modern muskox both a great reference genome and suitable surrogate for a clone. As such, the Harlins Muskox goes into S tier. Now, let's take a look at some other Ice Age ungulates, starting with the western camel. This was a species who lived in North America during the last Ice Age. It was a descendant of the common ancestor of all living camelids, a group which includes llamas and camels, but not a descendant of the last common ancestor of the living Bactrian and dromedary camels, having split off from their lineage some 10 million years ago. While the western camel lived in cool and semi-arid conditions, having split off from its closest living relatives that long ago would nominally put it in the boundary between D and E tier. However, modern camels can hybridize with the even more distantly related guanaco via artificial insemination. This suggests that camelids have a much more conserved genetic architecture than most other similarly aged mammalian families, and that the modern camels would be both a good reference genome and surrogate for a western camel. So it gets moved up to C tier. In Eurasia, there was the iconic Irish elk Megaloceros, with the widest antler span of any deer species. It inhabited the mid-latitude parts of Eurasia, i.e. far north enough that the cooler environment could preserve DNA in bones, but not far north enough to walk over permafrost. Hence, we likely won't find any ice mummies from it. The Irish elk's closest living relative is the fallow deer, having split off from it 5.8 million years ago. With DNA in a similar state of preservation and comparable divergent state with its closest living relative, Megaloceros goes into D tier with the direwolf. The North American equivalent of the Irish elk was arguably the giant stag moose. While the Irish elk was not an elk at all, the closest living relative of the stag moose is the modern moose, having shared a common ancestor with it about 1 million years ago. This, along with the fact that it inhabited cool regions which would have preserved its DNA, puts it in B tier. One group of ungulates who were much more widespread during the Pleistocene than they are now are horses, with many species of the genus Equus living throughout Eurasia and the Americas. For the most part, it's pretty difficult to figure out where to draw the lines between extinct species and which could simply be subspecies of living wild horses and asses. However, a major division seems to be between those who lived in the Americas and Eurasia, a split which occurred roughly 800,000 years ago. Because of this, we can safely say that those in the Western Hemisphere are distinct species from any living horses. So, I'll discuss these for this video. Some, like the Alaskan and Yukon horses, live close to the Arctic, and we found their mummified remains in permafrost. Because we can get high-quality DNA from them, and they were about as closely related to living horses as the cave lion was to the modern lion, they will go into the S tier. Since most other horse species in the Americas lived in areas that were at least decent at preserving their DNA, we can use the stacking resurrections approach once we get the Beringian species back, so they'll go into A tier. Apart from the genus Equus, there are two other genera in the Americas: Harrington Ahippus in North America and Gipadon in South America. Between these two, Harrington Ahippus was more closely related to modern horses, but not by much, having shared a common ancestor with them about 5 million years ago. Both had ranges which extended into high temperate latitudes, i.e. the Dakotas and Patagonia during the last ice age, where the cooler and semi-arid conditions would preserve their DNA. However, since they branched off from living horses as long ago as they did, there will be difficulties cloning them using any living horse as a base, so they'll go into D tier. In South America, there are two enigmatic groups of ungulates, the bulky rhino-like notoungulates and the gracile horse-like lidoterns. The most well-studied notoungulate which survived into the late Pleistocene was Toxodon. It lived in warm, humid environments which would have quickly degraded any nuclear DNA left in bones, so it's an easy F tier. Where to rank the most famous late Pleistocene lidotern, Macrauchenia, was tricky. Its range extended down into Patagonia, where the cold, dry conditions would have preserved some nuclear DNA. However, it's believed to have split off from its closest living relative, the Perissodactyls, horses, rhinos, and tapirs, over 60 million years ago. Between then and now, the genetic architecture would have changed so much that you may not be able to reconstruct Macrauchenia's genome from fragments using any living animal as a reference genome. So, while I want to put it in E tier because we can get some nuclear DNA, it is so distantly related to any living animal, I have to put it in F tier. Apart from the ground sloths, another bizarre group of Isnarthrans which lived in the late Pleistocene and early Holocene were the Glyptodons, with several species living in the Americas 12,000 years ago. Most of them lived in the northern part of South America, i.e. a hot, humid region. However, some species like Glyptodon had ranges which extended into the northernmost part of Patagonia, and conversely, Glyptotherium had a range which extended into the border regions of the US and Mexico. While far from ideal for the preservation of genetic material, the climate in these regions can allow Ice Age nuclear DNA to last to the present. However, it will certainly be highly fragmented, and this is compounded by the fact that the Glyptodons split off from their closest relatives, the fairy and Taliputinian armadillos, over 40 million years ago. This will make reconstructing their genomes extremely difficult, if not impossible. This puts all the Glyptodons in F tier. While when they think of Ice Age beasts, few people will think of rodents, but some, like the giant beaver, reach the size of the modern black bear, making them larger than the largest living rodent, the capybara. As its name suggests, the closest living relative of the giant beaver is the modern beaver, with the two having shared a common ancestor about 9 million years ago. It was difficult to decide whether to put it in D or E tier. The giant beaver did split off from its closest living relative earlier than the direwolf did, and it lived in more humid conditions, i.e. the Midwest, but it also lived in cooler climates than the direwolf did, so in the end, I decided to put the giant beaver in D tier. Last, we'll look at the megafauna of Australia, which includes giant wombats, kangaroos, monitor lizards, duck-like birds, and of course the ferocious marsupial lion. There are a number of factors working against the possibility of cloning any Pleistocene megafaunal species from Australia. For one, there is their age. In the northern hemisphere, most of the megafauna who went extinct did so between 15,000 and 10,000 years ago, while in Australia, most died out between 40 and 50,000 years ago. Second is the warm climate of Australia. The continent does include vast arid regions such as the outback, but the megafauna were most abundant in semi-arid to moderate climates. These two factors would degrade any megafaunal nuclear DNA in bones, and most of these bones are already partially fossilized. While caves in the Nullarbor region have preserved soft tissue via desiccation, we haven't found any mummified remains which date back to the Pleistocene-Holocene boundary, let alone 4 times older. And, even on the off chance that you could get any nuclear DNA, most Australian megafauna are more distantly related to any living species than the majority of fauna in the Northern Hemisphere. The short-faced kangaroo Procoptodon split off from living kangaroos over 20 million years ago, while the giant wombat Diprotodon, the marsupial lion Thylacoleo, and the marsupial sloth Palorchestes split off from living wombats around 40 million years ago. For Guineornis, its split from ducks might be older than 60 million years, although Megalania could have split from a modern species of monitor lizard more recently. But again, there's no DNA to work with, so all Australian megafauna will go into F tier. Well, there's my tier list. Sorry if I missed any species you were interested in, but I couldn't cover all extinct Pleistocene megafauna in a single video. If you have something you'd like to add or disagree with me about something I said, please leave a comment. As always, if you enjoyed what you saw, please like and subscribe. Thanks.